Okay, this screencast is to look at the step response of a system that has dominant complex poles, but we're going to question that dominant assumptions by having a nearby real zero. Okay? I'm sorry, a nearby real pole. All right, so let's take a look at the situation that we're talking about. I'm going to draw the j omega axis. I'm going to draw the real axis. I'm going to put a pair of complex conjugate poles. And if you'll remember in our second order model, the real part here is sigma, and sigma is equal to zeta omega n. But we're using normalized frequency here, so we're going to let omega n equal 1. So basically sigma is equal to zeta. All right? So the question is, what happens when there's a real pole that's added to the closed loop transfer function? And this can happen by the way we design our controller. All right, so through a feedback mechanism and the way we set up our controller, we can generate extra poles and extra zeros. And we're curious about what happens to the step response in these cases. Okay, so here's what we're going to study. We're going to look at what happens as you add poles along this real axis. Okay, so the first place you might think of adding it is right here at a location where the extra real pole is at sigma. All right. So if we did that, we could calculate the step response and see what happens. We then might be also interested in seeing what happens when we move this pole location. It's hard to move it, so I'm going to redraw it. We move this pole location a little bit further to the left, okay, and then move it yet again further to the left. And as we move it back this way far enough, it should look like the regular second order response. Okay, and so the way we set this up, let me clear some things up here, is we will make our transfer function fit a certain form. Okay, so you can follow along in the book and read about this as well. So what we're doing here is we're taking the second order transfer function, we're letting omega equal 1. So writing out the second order equation, we have s squared plus 2 zeta s plus 1. Remember, omega n is equal to 1. And then we're adding a real pole. Okay, and the way we're going to do that is we're going to add this at s divided by alpha times zeta omega n. But remember, omega n is equal to 1, so it's really s over alpha zeta. Okay? And so what this does is it gives us a knob to turn, a knob that we would call alpha. All right? So if I make alpha equal 1, then essentially what we get is a additional pole at sigma. All right, so let me show you why that would be the case. All right, we've added this term to the denominator. Okay, so I'm wondering, how does that generate a pole? So I would take this expression, set it equal to 0, and solve for s. So s would be minus alpha zeta omega n. Okay, and then we let that equal 1. All right, so if I put alpha equal 1, then we see we have a pole at s equal minus zeta, which would be, of course, right here. All right? And so we could change different values of alpha. If we put alpha equal 0.1, that would move this over close to the j omega axis. All right? If we put alpha equal 2, this would put this over here at 2 zeta, and we could look at the effect then. So as you see, we're going to change alpha. All right, let me grab this. We're going to change alpha. Okay, as we increase alpha, so say here would be alpha equal 0.1, 0.2, and then we march along to alpha equal 1, alpha equal 2, alpha equal 3, alpha equal 4, and so forth. As we move back to the left, this should look more and more like an ideal second order response. So the question is, what happens in the meantime? All right, so that's the setup. I'm going to go to MATLAB next, and we're going to study the output response when we have a nearby real pole. Okay, this is a MATLAB script to plot the step response for the case where we have a second order dominant pair of poles. We say dominant, but it's not necessarily going to be dominant. But we're looking at what happens between the ideal second order response versus when we have a pole that gets nearby. Okay, so I had this set up where the very first thing we do is we calculate the step response for an idealized case. All right, and then we go ahead and plot that and pause it so that we can get that up on the screen to take a look. I had this set up with line width being 4, so that this ideal case will be a little thicker. And then this display name thing is just a way of setting up the legend that shows that this would be the ideal response. Okay, as we move down in this file, we're comparing this to a step response that has a 0 location. Okay, so in the first part of this video, we talked about if I take this term, S divided by quantity zeta plus alpha omega n, but omega n is 1, then there's a pole, a real pole that's generated at zeta times alpha. All right, so as we change different values of alpha, which is given here, an alpha value of around 0.1 is close to the origin, and then we move from the origin back to the left in steps as you see here. Okay, so I can run this and I can take a look at the effect. All right, so let's take a look at the step response. I hit run. There's the ideal response. We're seeing that here. Now, when you have alpha equal 0.1, alpha equal 0.2, you see these are overdamped cases, and as we move closer and closer to alpha equal 1, it becomes more like a critically damped case. As alpha moves further to the left, you start seeing some oscillation occurring, some overshoot occurring, and as you move alpha further and further to the left, this starts to converge back to the ideal step response. So you can see some general effect here. The general effect is if we add a real 0, the closer we have it to the 0, or to the excuse me, to the origin, the slower our response is going to be. This is quite slow, probably, an unacceptable response. All right, as we move alpha closer and closer to sigma, we start to get overdamped cases. Again, the rise time's not very good here. The settling time's not very good here. And so you might want to keep moving back towards, higher values of alpha. All right, so in general, you see the effect. If we have that real pole, it's going to reduce the overshoot, but yet also reduce the rise time.